Hello everyone, today we will start our third module for this F1TENTH class, which is the localization and mapping. I will be responsible for today's lecture and Wednesday's lecture. So the lesson plan is as follows. Part 1 will be an introduction to state estimation, and part 2 will be the recap of some concepts in probability, like the law of total probability and Bayes rule. Part 3 will be the introduction of the recursive Bayes filter, and part 4 will be some variants of Bayes filter, like the Kalman filters family and the particle filter. In part 5, we will introduce how to tune some parameters for the particle filter we actually used in ROS2. So first is the state estimation. From last week's lecture, we introduced how to describe our dynamic system, so our F1TENTH car, with a series of original differential equations. We introduced the kinematic model of the car, which is a single-track model, and we also introduced some vehicle states like the position, the speed, and the acceleration. However, for last week, we primarily focusing on the forward path of this system. That means if we have the control input, in our case, the control input is given by the torque of the motor, which gives us the speed of the car, which gives us, actually, it gives us the acceleration and then gives us the speed of the car. And if we have the control input, how can we get the state of the systems by the system matrix and the input matrix? And then if we have the state of the systems, how can we get the output by the output matrix? So for the output part, we have our sensors. One is the IMU, the inertial measurement unit, comes with the VESC. The IMU can give us a measurement of the speed and accelerations in each axis for the car, but it's not very accurate. And also we have our LiDAR, which will give us a range measurement from the car to the obstacles or the tracks in the map. So the LiDAR, we will use LiDAR for the localization and mapping. We know that there are also other sensors, for example, the GNSS, which will give us the GPS signals, and a camera, which we will use for our Lab 8 Vision Lab. So all the sensors, they are output of our systems, but up to now, we are primarily focusing on the forward path. So we have the control input, and then we infer the state of the systems, and we have the state of the system, then we infer the output of the systems. But in the real world, it is often the case that we do not know the state of the systems, and the only thing we know is the control input. And the only thing that we can observe is the output of the systems. So that gives us the question of state estimation, which in this class, the state is the position, and our estimation question will be the localization. Localization questions. So the first question will be, since we already know that there is always a forward path from the control input to the state of the systems, then why can we just use the control input? So we just use the control input and we have our initial state, then intuitively we can infer the whole trajectory of the car. So actually, this is a method called dead reckoning, and it is widely used for the navigation, for example, for the navigation for a plane or a ship in real world. So the definition is, if we want to calculate the current position of the car, we can use only the previously position, and we incorporate the estimation of our speed, heading, and elapsed times. So let's take a simple 1D example here. If we know our car is start at x equal to 1, and then our speed estimation is 1 meter per second, then if we are 100% sure about this estimation, so if we know exactly that the car will start at x equal to 1, and we know the speed is exactly 1 meter per second, then it's fine. We can say that after 1 second, the car should be at x equals to 2. So that's the case if we have a perfect estimation and a perfect kinematic model. However, I think as you can see from the parameter tuning last week, there is always uncertainty in the measurement and system model, which will create cumulative errors. So the error itself it seems to be negligible if the time range is very small. So if the actual velocity of the car is 2 meters per second, and our estimation is 1.9 or 2.1, then in a very short time, there is not much deviation from the true trajectory and the estimated trajectory. But as time stepping, this error will become more and more large, and the estimated trajectory will be deviated from the true trajectory. So for our F1TENTH car, we estimate the speed from the electrical RPM of our motor, and we tune the offset and the gain for this motor. But when we echo the odometry topic of the car, we can still see that there is a differences between the actual distance the car traveled in the real world than our estimation. So to explicitly express this uncertainty, we can use probability. So instead of saying that the car is exactly at some position, we can say there is 80% chance or 90% chance that the car is at that position. In this case, we can frame our state estimation as a question to approximate a distribution of the position. That means we can use mainly math tools we know from the statistic course, and we can use them to estimate our state distribution. So let's recap our question problem setting for the state estimation. In this case, we know the control input, which will give us the dead reckoning, the prediction of the next state of the car. And that's not enough. We also need the observation, which will give us a correction of the for the current estimation. So combine those two steps, we will know how to approximate the posterior distribution of the current state. Then let's recap some concepts of probability that will be we were used for the deduction of the base filter. The first is the conditional probability and base rule. We know the definition of the conditional probability is that the chance of event B when event A has already happened is denoted as probability of B given A. And then we can get, if we know the probability of event A is PA, and we know if event A has already happened, the probability of event B that also happens is PB given A. So intuitively, we know if we times PA by PB given A, we will get the joint probability, which is PAB. Next, we will just do some simple metric. Let's say we leave the conditional probability on one side of this equation, and it's the left-hand side, and the right-hand side will be the joint probability divided by the margin probability. And for the next step, we substitute the joint probability by the second equation from part 1 here, and we will get the expression of base rule. So this is just some math-like manipulations, but the explanation behind the base rule that is this formula provides a method to estimate, to update the probability of some hypothesis given an event that is related to this hypothesis. So let's say in our case, event A is the measurement, and event B will be the state of the systems. If we do not have any sensors, if we don't know any measurement, if we don't know any measurement from the sensors, then we have a prior, which means that if we don't have any other information, what's the probability of our state? What's the distribution of our state here? And the likelihood is that if the state is actually at some certain value, so if the state is actually at some value, then then what's the probability that we get this observation? So that's the idea of the likelihood. Then the margin probability is just like a normalization term, and using the information from this evidence from our measurement, we can update our estimation for the current state. So this is called the posterior distribution, and we can also call it a belief in our state estimation problems. Another important concept is the law of total probability. So it is always easier to start with the discrete case. Let's suppose B1 through Bk are mutually exclusive and exhaustive events in a sample space. Then for any event A in the same sample space, we can know the PA is just the summation of all the intersections between A and B1 through Bk. So from the definition of the conditional probability, we can just substitute the intersection term with the multiplication of the conditional probability and the margin probability, and we can rewrite this expression into a summation of the conditional probability. For the continuous random variable, we know instead of the probability mass function, which just say that if the random variable is exactly equal to some value, we have the probability of that. So instead, continuous random variable can take infinity numbers of values, which means that if we want to estimate the probability of a continuous random variable that fell into a certain range, we can use the area under the probability density function. So, for example, the area under the curve between point A and point B will give us P, the probability of X fell into the range between A and B. So also from the calculus class, we know if the range is small enough, if we just have a tiny range, then we can estimate this the probability of X fell into this tiny range by just multiply the probability density function with the span of this range. So use this differential element, we can get the integration form of the law of total probability for the continuous random variable. So here, instead of the summation, which is a discrete case, we will have the integration. Up to now, we only introduce up to now actually we use discrete events to describe the base rule, and we only use two events. So in our case, event B is the hypothesis, and event A is the evidence. But in real world, it is often the case that event B depends on many other conditions, like C1 through Cn here. And if those other conditions are the historical information, then we will get the definition of the recursive base filter. So our mission here is that we want to know the belief or the posterior estimation for our state, and what we have here. So what we have here is a string of the observation of our sensor measurement and also our control input. So we have the observation and the control input starting from timestamps, like starting from the beginning and up to timestamp t. So given those information, how do we estimate the distribution of our global state? And then we can give a more systematical problem setting for this recursive base filter. We know we can use so for these dynamic systems, it's time varying, so we can use a hidden Markov model to describe these systems. We have a series of states, which is the X, and we have the control input, which will influence the state, and we have the observation, which will be influenced by the state. So the action model describes how, like, given the previous state, given the current control input, how can we get the next state of the systems. So basically, it is just what we do for the dead reckoning. And another model we have is the sensor model, which is the likelihood of the sensor. So this model is called hidden Markov model. Is that first, we know the Markov property is just like a conditional independence, which means the future is only depending on the current state, regardless of the past. So that means for our sensor, if we have the current state, then the likelihood is independent of the past states. Also, if we have the current state, then our future state is independent of the past state either. It is called the hidden Markov model. Also, the hidden term is from the fact that we cannot directly observe the state of the systems. The only thing that we can observe is the observation, which are the sensor data. So it's like the state itself is hiding behind the observation. So that's why it's called a hidden Markov model. And then in our case, the action model tells us how to use the control input, and the sensor model tells us how to combine the observation. And we will break down our mission for the base filter into 2 steps. Step 1, use the action model to do the prediction, and step 2, use the sensor model to do the correction. So the first step is the prediction with the control input. The brief here is that we want to estimate the distribution of state x xt, and what we have is now is the observation up to time minus t up to t minus 1, and the control input up to t. So what we can do is to apply the law of total probability. We know for a state, all of the possibilities that it can be transferred from the state of the last time step. So if we sum over all the all the possible states from timestamp t minus 1, we can apply the law of total probability and use the integration notation for this equation here. And we know our estimation for the last timestamp t minus 1 is just our belief for the last timestamp. So here we will get a recursive terms about how to use the belief of last timestamp to get the prior estimation for the current timestamp. And also then we can apply the Markov property here, because if we know the information of x t minus 1, then we can just abandon all the other useless informations of the observations of all the control input. So we only care, the only thing we care is the state estimation from t minus 1 and the control input in for timestamp t. That gives us the prediction step, and this term is just the state transition part, which is our action model. Then step 2, after we predict the state for the systems, the next step is to do some correction with the observation. So here we will put our observation at timestamp t into consideration. So what we have here is that we can use the base rule. If we apply the base rule to this equation, we will get the first term is the likelihood, the second term is the prior distribution, and the denominator here is just a normalization term. So again, we apply the Markov property to simplify this equation, and we will get the sensor model here. Since the posterior is a property distribution, then we can then for the normalization term, we don't have to actually calculate like the probability of observation t given the observation and the control input stream, we can just as long as we know the posterior is in proportion to the likelihood times the prior, then it is okay. We can just normalize it afterwards. So this gives us the basic idea of the base filter. So step 1 is the prediction. Step 2 is the correction. However, in practice, we know it is always difficult to use just use this form of the base filter. So if we want to filter, if we want to apply the filtering algorithms, it is always the case that we use our the extended Kalman filter or the particle filter instead of the base filter itself. So the reason here is because that the basic form of base filter need to do a multiplication and even integration of two probability distributions. So let's just assume that we have a very complicated distribution, and so we will have a complicated probability density function. In this case, this question can be untractable because every time you multiply and integrate two probability distributions, you will make this PDF more and more complicated, and you may not have a stable analytic solution. So that's why the basic form of base filter only appears in some homework practice for your for your ESE 650 learning robotics class, and in practice we use the variance of the base filter. The first idea is that since we know the distribution itself can be complicated, then why not we just use a very simple distribution and assume the state and noise all follow this simple distribution. And of course, we will use the Gaussian distribution here. This assumption actually gives us the big family of the Kalman filters. The good thing about Gaussian distribution is that first, if two sets of variables are jointly Gaussian, then the conditional distribution of the set conditioned on the other set is again Gaussian. The second probability is that the Gaussian distribution is self-conjugate. So given the Gaussian likelihood function, if we choose the Gaussian prior, we will also result in Gaussian posterior. That means that so these two property give us actually it's a very good estimation, because every time we multiply two Gaussian distribution or we use the base rule to estimate the posterior of another Gaussian distribution, we will still keep the same form of distribution throughout the propagation, and we will find an analytical solution. If you so this is calculate, so we can calculate the Kalman gain for the Kalman filter. I will just skip all the mathematical proof here, but you can always find there's a lot of resources on the internet, and I just want to show that if you assume the state and noise follow a simple distribution, you can find an analytical solution for this base filter. However, another method we can use is just more like a brute force method. So instead, since this distribution itself is very complicated, so instead of calculating the PDF for this distribution, we can just use sample-based method to estimate the distribution. So that's the idea of the particle filter, which we were introduced for our Wednesday lecture. And then for today, we will take a quick example for the extended Kalman filter, just to let you to better understand the process of the base filter. So it is a 1D example for a car, and the state here is the position of the car. Our observation is actually the measurement from the sensor to a pole on the car, and our assumption follows the assumption for the Kalman filters, is that both the state and the observation follow the Gaussian distribution. Let's take a close look for the measurement model. So one way is that we know the configurations for the sensors. So let's say we know the covariance matrix for these sensors, and then we can just use this module for the, like we can just build a Gaussian distribution based on the configuration for the sensor. But sometimes we do not know the we do not know what exactly the variance is, or exactly the how uncertainty the sensor will be. Then we can just do a simple test. So we take a lot of measurements with a static car. Then we can estimate the Gaussian distribution. So first we can calculate the expectation, which is the mean of the measurements, and then we can calculate the variance. We can calculate the variance of this distribution, which is the uncertainty, and then we can fit the Gaussian distribution model into those sample data points, and we will get the sensor model for this measurement. Okay, so we will start at the initial state. The initial knowledge of the systems at time t equals to 0 is shown in figure 1. The arrow pointing to the right represents the known initial velocity of the car. So as we know, the step 1 is just prediction with the control input. So the prediction of location of the car at time t equals to 1 and level of uncertainty is shown in figure 2. We can realize that the confidence in the knowledge of the position of the car has decreased, because we know there is always a gap between the control input and the actual action taken by the car. So as the car is moving forward, as the car is moving to the right, our confidence will decrease, because we know there is always the cumulative error, and we will be more and more uncertain about our estimation. So that's how the measurement come into play. So for the step 2, we will correct our estimation, so our prior estimation, the prediction, with our observation. So in figure 3, we can see the measurement of the location of the car at time t equals to 1 is given by the blue Gaussian block, which is also noise, and the level of uncertainty, it has a certain level of uncertainty here. And now we have the orange. Orange distribution, Gaussian distribution. We have the blue Gaussian distribution. Then we can just combine those two distributions together, which is the times the likelihood and the prior, will give us the proportional result for the posterior. So if we just combine those two distributions and we normalize the new distribution, we will get a new probability density function, which is the green one here. And this gives us the best estimation of the location of the car by fusing the data from the prediction and the observation. So this is just one time step for the base filter, and we know if the car keeps moving, then this green distribution here will be treated as the initial state, just as we did for the system at time t equals to 0 here. So we will keep this filtering again and again for each time step, and we will get a stream of estimation for the state. Okay, so this is another extended common filter example, which is animation. So as we can see here, the blue line is the true trajectory, and the black line is the dead reckoning trajectory. The green points are the positioning observation. So here the observation is actually given by some GPS signals, which shows a certain position of the car. And the red line is the estimated trajectory with extended common filter, and the red ellipse here shows the estimated covariance with the EKF. So at the beginning, it can be very noisy because the measurement itself has some deviation from the true trajectory. So but as time stepping, so the estimation become more and more accurate, and the convenience of the EKF is decreasing. We can also see from the dead reckoning trajectory here, and we can see the error is accumulated. So even if at the beginning the trajectory seems fine, so it follows the true trajectory, the blue line here. But so as time goes by, the extended common filter will be more and more confident, and there is also a scaling with the whole animation. So in a larger scale, we can see the estimation of the common filter is better than the dead reckoning. Okay, so let's just a simple example of the extended common filter. And this idea is also widely used in our localization problems, but there is another powerful tool we can use for the localization, which is the particle filter. And we will introduce the algorithms for the particle filter on Wednesday.